Hello everyone, and welcome back. So this time we're going over a more complicated example. Last time we had two simple shapes, a rectangle and triangle, and now we're going to see what we do when they're put together. Now I kind of gave away the steps here, but it's not easy to see unless you can actually see an example. But in the end, this problem is actually very simple. We're just going to turn our integral into a sum. Now I've given away too many hints already, so hopefully you are prepared to try out this example on your own. So, as always, I'm going to give you the plan, then you're going to go off on your own and do it. So first off, you can divide this distributed load into two parts, one rectangular loading and one triangular loading. And you also know where the resultant force of those two parts acts. So you can find the total resultant force from adding those two together. And then you can figure out where that resultant force will need to be placed by summing your moments. Okay, so giving you the hints, pause here, go try it on your own, and then in 3 seconds, you're gonna come back and we're gonna do it. Or at least in my 3 seconds, your several minutes. So 3, 2, 1, and here we go. So let's get to it. So the first things first, we have two resultant forces. Resultant force 1 and resultant force 2 right here. Now this is a rectangular section and this one right here is triangular. And so we know we just need to find the area under those two curves. We're going to do it separately though. So first this one right here, it's got a max of 150, so that's its height. Its base is 6. So 6 times 150 is 900. We divide that by 1/2 because it's 1/2 base times height. So 450 pounds. Where does this apply? Well, that applies 4 feet from the edge because it's always 2/3 from the point or 1/3 of the distance from the base. Rectangle, it's even easier because it is just a rectangle. Base times height, so 8 times 150 gives you 1,200 pounds. And where does that apply? Well, it's going to be halfway from the edge, which is 4 feet, but we're going to go from point A, so 6 plus 4 is 10 feet from point A. Okay, now here's where it gets really simple. You've gotten rid of those distributed loads. All you have now are forces. You've done problems before where you just had forces. And so just do it the same way. We're going to move these to the origin. We're going to calculate a moment from that. And then from that we can eventually figure out exactly where it would need to be placed to have the same effect. Now, this is a slightly different thing, but you can see the same thing here. It's telling us what the moment would have to be at here for these two forces to be applied there. So 4 times 450 and 10 times 1,200, because I'm moving this 1,200 force all the way 10 feet, and this one only 4 feet. It gives me this large number. Now, if I add these two forces together, and I put them in a single point, it has to still cause that same moment, which means it's actually fairly simple to calculate. So my resultant force times x, our centroid, has to equal our moment around point A. Also, it has to equal our moment around B if we had calculated it differently. And so what we get from that is that if we're going to sum this, we take a resultant force, which is 1,650. We have our moment, which is 13,800. And we divide 13,800 by 1,650. What do we get? We get that our centroid is 8.36 feet from A. We could have also done the exact same thing with everything going from B. So you have to be very careful that this is no longer 10 feet away, it would just be 4 feet away. And this one is no longer 4 feet away, it would be 10 feet away. So, I hope this helps you. And we'll do one more example on this next time to hopefully really drive this home. So, I'll see you all then. Have a good day. Bye-bye.